And of course, it's always a pleasure to come back to beautiful Rio, right? As I told Maria, any excuse to come to Rio, I'll take it, right? Without having to think at all about it. So it's great to be here, and it's been a wonderful conference. So what I'm going to be talking about today is, in a way, certain things I'll speak go along the lines of what Carol spoke yesterday. Some will go along the lines of what Décio spoke, but I'm going to give a little twist, along the way. So part of the idea is to think ways in which anomalies can actually be extraordinarily important to scientific development. That's one of the things that Ray highlighted yesterday. And that also reminds of ways of accommodating these things. So, and I'm going to look at in particular, one example of when anomalies are especially productive heuristically, and try to draw some consequence from it. And also consequences for those who think that, for example, mathematics is indispensable. And if those things are indispensable, they should tell us something about the way the world is, right? And I'm going to say that there is some troublesome problems for those who believe in that view, exactly in the context of discussions of anomalies. So let's see how that goes. All right. So anomalies, as we all know, are context dependent, right? In one context, something may be considered anomalous that it's not when you change the context, right? So, example that we also already discussed, the perihelion of Mercury. It's a problem for Newtonian physics. Turns out to be something that relativistic physics deals with it very well. So what I'm going to do is try to examine the conditions under which inconsistencies may not be thought of as being anomalous, right? And I think part of the issue here is thinking about the plasticity of the concepts, right? They have to have content, they have to rule out certain things, but also they have to be malleable, right? In ways that allow us to express in a straightforward, intuitive way certain things. So, and that's what inconsistencies actually can be very, very good at, provided that we know how to handle them. And in that case, some of them may not actually be anomalies at all. So I'll then examine, as an illustration, the early formulation of the calculus, right, in the hands of Leibniz and Newton, and the use of infinitesimals, right? And think about the processes that make that so successful, right? And also the conditions under which it may have been seen to be anomalous, even for those who developed, right? Leibniz himself thought, okay, to the horror of L'Hopital, that infinitesimals are useful fictions. And L'Hopital couldn't understand that. Well, you made those things up. What do you mean they are useful fictions, right? So we tried to understand a little bit what was going on in the situation that put some pressure for Leibniz to think of that, right? And then having some clarity about these non-anomalous inconsistencies, I'll try to indicate that they put some pressure for those who think that indispensability considerations are a good argument for your ontological commitments. Right? And the result, hopefully, will be a sort of distinctive understanding of anomalies, at least in some specific context. All right, so let's see how this goes. Now, there are three different, from the philosophy of science, three different conceptions of anomalies. Interestingly, Carol yesterday talked a little bit about some of those things. I'll present similar ways. So first we have Kuhnian anomalies, right? Those are puzzles that a paradigm was supposed to be able to solve, but cannot, right? Yesterday, Carol distinguished puzzles and anomalies. I actually think that Kuhn runs those things together. There are certain things that may be initially thought of as puzzles, and eventually, if they become recalcitrant and no one has a clue about how to solve them, they may, after enough of those things accumulate, become anomalies. right? Lakatos has, a different understanding. So basically, predictions that a research program was supposed to make but fail become anomalies, right? And Loudon has, I think, the most interesting of all, right? So you only have an anomaly when you have a research program, a research tradition, which are broader, even broader than research programs, in his view, that solves a problem, and a rival tradition fails, right? So it's only in the context of a relative theoretical context that something can be thought of as anomalous. Now, all of those conceptions on anomalies are deeply theoretical, theory laden, right? They depend fundamentally on conceptions like paradigms, research programs, research traditions. They don't even make sense when extracted from that context, right? So you cannot even express what they are, without referring to the very theoretical context. So this is coming here, in which they were put forward, right? So, and if you think about paradigms, research programs, research traditions are all clusters of theories together with additional stuff, right? That's one of the features of philosophy of science done from the 60s to the 80s. You say, well, theories are too narrow a scientific unit of analysis. You need broader things, right? So you need theories plus, in the case of paradigms, values, goals, methods. In the case of research programs, you need hardcore, right? Certain the hypotheses that are preserved no matter what. You need positive and negative heuristic rules about how to deal with falsifying instances. You need protective bounds, bunch of series of hypotheses to protect from falsifications. And with Loudon research traditions, we have broad ontologies and certain methods to solve problems, right? So all of those are very large scale, right? Highly theoretical reconceptualizations of science. I think they are wrong, right? This is too much stuff, right? What you have here is a sort of a piece of philosophical fiction, right? We're a big scale. Well, we need all these extra stuff to think about the science. And then you're miles away from the actual scientific practice. Scientists deal with this particular hypothesis, context problems that are very well delimited, otherwise things get out of hand. They make idealizations over specific things. So I think this is a philosopher's law of theories. So they're sort of projecting onto scientific practice a bunch of stuff that it's actually not necessary. Now, for our purpose today, the problem with that is these ways of thinking mess up with the very idea of what anomalies are, right? I think if you think about scientific practice, it's far less unified, far less theory-driven, and much more loosely structured than any one of those highly theoretical descriptions would suggest, right? So, and then for us, why that matters in the context of thinking about anomalies is we now have a picture of anomalies that suddenly they are these, well, driven by theories, all right? And only expressible in terms of those frameworks. And I think that's not right, right? What I'm going to try to suggest is anomalies, as so much of science, is piecemeal. It's connected to specific problems. And it's that context, right? The context is very limited, that will make something anomalous or not. So we need to look at the details rather than the big picture. So I think Carol was right, for example, yesterday when she looked at a whole bunch of examples, right? Very specific, each one of them with their own specific contexts, right? Now we are going to do the same thing, considering one example, right? Now, what should we think then about anomalies? So here's a simple-minded way of thinking about it, right? Rather than framing it in terms of this broad theoretical concept, think about an anomaly as an inconsistency within a problem situation. Right? Don't need to talk about theory. What theory, if theories are relevant, depends on whatever the problem situation is. Right? There is some kind of tension. Right? That's what makes it an anomaly. Now, how significant it is how exactly the details of that problem situation is going to unfold, right? Because I actually think that anomalies can be extremely positive in terms of the heuristic capabilities that they allow. But the theory-driven understanding of anomalies will force us to think of them in very negative terms, right? So, for example, anomalies are then typically understood as involving lack of puzzle-solving effectiveness, right? That's one of the Kuhnian understanding. They're involved with empirical falsification, as Lakatos will have, or some kind of conceptual difficulties in Loudon. So all very negative, right? Now, what I want to say is not only anomalies can be crucial in helping us open up for consistent successors in the face of inconsistencies, but more importantly, they may help identify opportunities for heuristics, opportunities for problem solving. In fact, the only way of solving some problems is exactly to explore an inconsistency. And I think the early calculus is a beautiful example of that. It has the features it has exactly because it's driven on top of an inconsistent conception of infinitesimals, right? Because what you have is, it's that inconsistent that allows us to express in a very straightforward, intuitive way, a notion that was crucial for the formulation of the calculus. It's not by chance that both Newton and Leibniz had an inconsistent conception of infinitesimals, even though they had incompatible conceptions of infinitesimal among themselves. One is a fluxions, the other is in terms of curves. So now I want to say that in the case in which inconsistencies are heuristically fruitful, there is a sense in which they are not anomalous. If you think about anomalies as being something negative, right? If you want to keep term, inconsistencies have to be anomalous in some way, keep it, right? But then bear in mind that some of those anomalies are actually positive, right? Now, I think part of the situation is because depending on the problem situation at hand, there might be consistency constraints in place that force people to say, well, we need to give up on those inconsistencies. So, but then the problem is not with the inconsistency, but it's with the norm that is guiding the research problem ahead, right? So let's think a little bit for a second about this idea of a consistency as a constraint, right? Of course, the requirement of mathematical consistency, right, claims that mathematical theories should be consistent. It's, of course, typical and find widespread in both pure and applied mathematics, right? Of course, it makes sense, right? It makes sense, especially if the underlying logic is classical, right? Because in that case, everything will follow from a contradiction. You get a trivial system, which is useless, right? So, of course, if the underlying logic is classical, intuitionistic, or any one that it's not very consistent, having a consistent constraint is reasonable, right? But not, why is it reasonable? It's reasonable because it allows us to have plasticity, right? What that means. Mathematics needs to have content. For it to have content, it needs to... An inconsistent theory running on the base of a classical logic has no content because everything follows from it. So it's trivial, right? So it has no plasticity, right? However, note what's interesting. An inconsistent theory whose underlying logic is paraconsistent, so it has more plasticity than a consistent one, because it allows for expression of possibilities that are foreclosed by logical machinery alone. So it's interesting, whenever you're thinking about changing a logic, the guiding constraints should be the following. So that, because not every change of logic, I think, is acceptable. Some are clearly ad hoc. You don't want to change a logic, say, okay, I have a problem here, I'm going to change the logic just that the problem doesn't come up. That's not a good reason. You change a logic when what you want to express is prevented by the logic that you have. So, for example, that's the argument that Dassey uses to argue for why you need non-reflexive logics to think about non-individuals in quantum mechanics. I cannot even express in classical mathematics that certain objects lack identity conditions. They will have, just because the mathematics imposes, plus classical logic imposes that. So to explore a possibility, an expressive possibility, I have to change the logic. Right? So that's, I think, it's a crucial idea. It's in that sense that an inconsistent but non-trivial piece of mathematics is more plasticity than a just consistent one, right? If you want to study properties of the Russell set, you cannot do that in classical set theories because it's explosive. But you can in an apparent consistent set theory. So what I'm going to do is then focus now on the role of this consistency requirement, right, in the context of mathematical theorizing, right, in one particular case. And then I'm going to consider what those who think that the mathematics is indispensable and therefore we should believe in the existence of the corresponding objects, will have to face in those circumstances, right? And I'm going to consider that by examining, ways in which theoretical considerations may force us to drop the requirement of mathematical consistency. And as will become clear, the situation is something very uncomfortable for the indispensability theorist. Okay, so just to be clear, what is the indispensability theorist committed to? Well, that's the indispensability argument. This is an argument that Quine formulated. Quine was a grudging Platonist. If he could have his way, he would be a nominalist, right? But he couldn't. He said, look, I cannot express, recognize how we can even express physical theories without mathematics. So, there's no way in which I can say, well, only the physics exists and the mathematics doesn't because I need the mathematics to express the physics. But then he says, but there is only one mathematical object, classes. That's all there is, because I can express whatever mathematic I want in terms of classes, and that's it, right? So and then the argument was refined. So actually, this argument has a very interesting history because Quine never actually expressed the argument explicitly. Who did it was Putnam. But then Putnam formulated an argument that Quine doesn't recognize. And Putnam himself doesn't endorse the argument, right? And to try to make everything clear, Mark Olivan then write down the argument in a sort of an explicit logical form, right? Of all of them, he's the only one who really endorsed the argument as presented, right? So here's the argument for what's worth, right? So we ought to be ontologically committed to all and only those entities that are indispensable to our best theories of the world. It turns out that mathematical entities are indispensable. Well, therefore, we ought to be ontologically committed to them. So beautiful, valid argument. If the premises are true, the conclusion will have to be true. The question is whether the premises are indeed true, right? As it turns out, I actually think that the second premise is true, right? There's no way you can dispense with mathematics if you want to do science and so on. That's Hartree-Field tried in Science Without Numbers. It's a phenomenal failure. What you get is a very awkward theory, right? You have to do all kind of maneuvering to mimic what? The plasticity of mathematics in some other terms. And then the whole thing becomes very artificial as a result, right? The problem, the second premise I think is true. The problem is the first one, right? As will become clear, right? But for those who believe that this argument, both premises are true, well, then they'll have to face an upward consequence, as I'll try to explain in a moment. Now, what count as our best theories of the world, right? Because that's crucial for the first premise of the argument. Well, those in Quinian ways, these are those who satisfy the usual, theoretical virtues. They're simple, they're explanatory, they're unified. They have all the nice features you may want. And if you have that, well, then there's no reason for it to be realist only about, say, electrons and photons, but not about vectors in a Hilbert space, differential equations, and so on. That's the force of the argument. All right. Now, what should then the indispensability theory say when you're faced with an inconsistent mathematical theory that plays a crucial theoretical role in physics? Well, suppose now that your best theory of the world invoke mathematical notions that are inconsistent, right? Now, so think about for a second about the situation. Let's go back, to the Leibniz and Newton time, right? So where Newton is developing his theory, and Leibniz, for other reasons, also developing a certain conception of infinitesimals. And so you have these objects, right, which are positive numbers, but it's smaller than any other number, right? So it's very interesting objects, right? Because they're positive, they can be divided, and on the other hand, because they're smaller than any other numbers, well, they're like zero, right? So they can be eliminated at the end. So they have a lot of plasticity. It's a very intuitive notion if you want to capture infinitesimal changes, right? Which is exactly the notion that they were grappling with to formulate the calculus. Now, of course, I think the case can be made that infinitesimals are indeed indispensable for that early formulation. As I said, it's not by chance that independently Newton and Leibniz invoke infinitesimals in their formulations, right? However, given the potentially inconsistent behavior of these objects, the introduction of these have been controversial from the start, right? And as I mentioned, even Leibniz said, well, infinitesimals are ultimately useful fictions, right? He thought that you just use them, but get rid of them afterwards. And the question is if you can really do that, right? Leibniz thought he was very clever in the way that he introduced and then tried to avoid, but I think at the end he couldn't avoid despite his best efforts. So his claim that the infinitesimals are just useful fictions are a little hard to be justified, as I'll try to illustrate in a moment, right? What's interesting, however, note that there's already a pluralism of interpretations of infinitesimals here, right? Because the interpretation of infinitesimals provided by Newton and Leibniz are actually very different, right? Newton thought of infinitesimal in terms of fluxions, right? They're sort of changing quantities. Leibniz thought of them as ratios of certain curves. He had a sort of a geometrical interpretation of infinitesimal, and they are very different kinds of things, right? Now, what kind of work do they do, right? So think about you have, a polynomial of this form, and then you have your formulation of differentiation where delta is an infinitesimal, right? So how can I apply this to this function? Well, just instantiate that the equation over the rule. You get this by doing simple algebraic manipulation. You simplify that way, and then the trick move, right? Because this is strictly positive. You can divide by it and get rid of a bunch of these delta. The only one left is this one, but this is smaller than any number. It's actually 0. You can just get rid of it. And you get exactly what you expect, right? Using the notion, right? So what's interesting here is it's the concept that it's very malleable, right? And does deliver exactly the result that we need, right? But of course, care here is crucial because since an infinitesimal delta, right, can be taken 0 in some contexts, we may have something like this, right? 1 times delta equals 2 times delta. If you assume that delta is 0, you can establish then 1 equals 2. So of course, that trivializes the entire operation. Right? Note that this is exactly the two uses that we made of infinitesimals in getting the right derivations. So one of the questions is, okay, but this is never an inference that we find in either Leibniz or Newton, right? So what was it that they were operating, right? That they prevent them from making an inference like that and didn't allow them to make the right inferences when making the differentiation of the polynomial, right? So you need care here about how to deal with that. Of course, the logic here cannot be classical, right? Because if it is classical logic, the notion is inconsistent. So you already have something trivial, right? Now, what Leibniz did was something actually clever. So use the infinitesimals to obtain the rules. And then when he was presenting the rules, he got rid of the infinitesimal, right? And that's what he thought allowed him to say, oh, the infinitesimals are useful fictions, right? Because you use them and then get rid of them, right? So when he formulated in the Novo Methodus, he didn't mention infinitesimals at all, right? And in that way, he thought, okay, I'm not gonna, he knew, of course, because the context he was operating on was a context in which consistency was taken to be a requirement by everybody else, right? In fact, including himself. He thought, okay, I better have some story about how I can get rid of the infinitesimals, right? So what was, he introduced them somewhat like algebraically, right? He just introduced a bunch of rules, right? Never bothered to prove the rules. He just said, okay, let's operate it in according to these rules. And the rules you get here is exactly those that you would expect, right? These are exactly the rules that just teach our students in a first calculus class, right? About how the derivative will go. Right? So, but no proofs, right? So sort of, it looks as though these things appear, from God's mind, right? So it's out of nothing, right? Whereas it's clear that he was using the infinitesimal to generate and think about these rules, right? It turns out, however, that when he explains what infinitesimals were, it's clear that when he explained the calculus, it's clear that he was reasoning and relying on infinitesimal. In fact, he was relying on a geometrical interpretation of the infinitesimal, right? In terms of curves, because if a curve is determined by the variables x and y, the x and dy will be infinitesimal difference, so differentials between the values x and y. In this case, what the way that Leibniz was thinking about is, well, this ratio here between the two gives us the slope of the curve at the corresponding point. So he was giving a geometrical interpretation of the infinitesimal, but then infinitesimals were there. Those are the magnitudes that he was operating, right? Also, the definition of a tangent, he uses infinitely small distances. So when he's flesh out what he takes the interpretation of the calculus, clearly the infinitesimals are there, right? So he didn't really got rid of them in effect, right? What's interesting is thinking about potentially inconsistent objects, he was able to get the right results, right? So that what needs to be properly understood, right? What is it that he was doing, right? That prevent the infinitesimals from being an anomaly, right? Now, he had a metaphysical conception. So, for example, if you read his discourse on metaphysics, you find at a crucial point a defense of consistency. He actually thought that consistency is a requirement for existence. Well, if you think that way, you would say, well, these things are inconsistent, therefore they don't exist, right? So he had a perfectly consistent conception of what he was doing. The question is, why is it that he never derived something like 1 equals 2, right? I leave this as a homework. All right. Now, let's think briefly about Newton. Newton also is a very interesting case here, right? In the section 1 of book 1 of the Principia, note what he tells us. It's actually very, very neat. Quantities and the ratios of quantities, which in any finite time converge continually to equality. So these quantities are different, right? They are converging to equality in a finite time. And before the end of that time, approach near to each other, then by any given difference, become ultimately equal. He's saying the two things that are different are the same, right? So you have two things that are slow, but they're approaching close enough, no matter what, they're the same. So you can see the notion, in that case, this very notion is inconsistent. And he clarifies later on. For demonstrations, short have to be divisible. So it's shorten the derivation using these methods. But because the hypothesis on divisible seems somewhat harsh, to say the least, right? They're inconsistent. So, and therefore, the method is reckoned less geometrical. I chose rather to reduce the demonstrations of the following propositions to the first and last sums and ratios of nascent and evanescent quantities. That is, to the limits of those sums and ratios, and so to premise, as short as I could, the demonstration of those limits. So this is his way of saying, look, I'm not going to bother you using the infinitesimals that I used to generate the calculus. Of course, Newton was clever, right? He was already introducing a notion of gravity in that book that flat out was incompatible with the accepted metaphysics, was action at a distance. He tried to explain that in terms of the accepted Cartesian metaphysics of the time, action by contact, couldn't, eventually gave up, and said, okay, this is what gravity is. Now, if he does that on the basis of a completely inconsistent theory, good luck, right? So strategically, he didn't use the infinitesimals, didn't present the theory using them, but they are clearly, presupposed in the way that he's already even understanding the behavior of those quantities. So similar situation, right? Now, how should then the indispensability theorist, right, approach what is arguably a mathematically inconsistent theory, such as the early calculus, given the infinitesimal, both different and identical to zero? So what do we say then? Remember, we are back, in 17th century, right? So the indispensability theorists will have to tell us, well, given that infinitesimals are indispensable to the early calculus, the indispensability argument forces us to be ontologically committed to those things and claim, yes, those inconsistent objects exist, right? But then the indispensability theorists will have to believe that there are true contradictions, right, as the dialethists would have it. Now, that would make Quine very uncomfortable, right, to say the least. And for many, this will be the very reduction of the entire indispensability arguments. Well, went too far here, right? Now we are being committed not only to mathematical objects, but we are committed also to inconsistent objects, right? That's too much to swallow. Well, alternatively, we could say, well, let's resist that conclusion, right? And say, look, if infinitesimal, we all know the story, right? It's going to be eventually dispensed with, right? When Bolzano, Cauchy, Weierstrass reformulate the calculus, in the 19th century. So no wonder, right? They were troublesome, right? But that doesn't quite explain, right? There are 150 years where you have, theorizing being done on top of those things, of these infinitesimals, right? So something has to account for the role that these things play, right? And as I try to indicate, it's not by chance that the infinitesimals were indispensable to the early formulation of the calculus. Now, what I think here, what we have here is a situation where you cannot just cherry pick, right? The indispensability argument, either it is ontologically committing, and then you're committed to the existence of true contradictions, or the indispensability argument is not ontologically committing, right? Given that you tell some story about why you infinitesimal somehow do not apply to the argument, but then you fail to support realism about the indispensable things, right? Now, some responses that the indispensability theorists may have. Say, maybe the indispensability theorists could resist the move and insist that, look, consistency is a minimal theoretical virtue, given that, you know, the early calculus doesn't even meet this requirement. Obviously, it cannot satisfy the indispensability constraint, so we are not committed to that, right? The problem is this just flies on the face of mathematical practice, right? As I tried to indicate, I don't think either Leibniz or Newton would have come up with the calculus the way they did without this notion. So obviously, they are being, right? And as I tried to briefly mention, when eventually you get rid of the infinitesimal with the reformulation of analysis in the 19th century, something is lost. Part of the intuitiveness of the calculus goes through the windows when you introduce epsilon and deltas. It's a very counterintuitive way to think about continuity. You cannot say what you want, namely, when the values of the function approach a certain, the arguments of the function approach a certain point, the value approach the corresponding point, right? So infinitesimally close. You cannot say that. You have to reverse. So no wonder students are confused, right? As I said, I think it's not by chance that the two formulations of the calculus involve infinitesimal. The plasticity of the concept was crucial for that, right? And you know, the familiar epsilon delta function, you know, of course, once you're familiar enough with them, so well, I think it's perfectly clear, right? But it requires some doing, which the original formulation does not. So what we have here is a trade-off, right? So less plasticity and more complex formulations, right? So you have something that is far more rigid, which is the later formulation of the calculus, and more complicated as well. So versus something that is more plastic but inconsistent. So you have to choose, right, where to go. Interestingly, we would not have had the calculus to be cleaned up if not because of those inconsistent notions. And that's my point, right? So that's where inconsistencies were playing a key role. Now, there's a rejoinder. On top of that, of course, the proposed response will require the indispensability theories to avoid commitment to something that is indeed indispensable, right? The infinitesimals. And that, you know, again, would undermine the support the indispensability argument is supposed to provide. Now, if commitment to infinitesimals is resisted despite their indispensability, basically, we are giving up on the realist reading of the indispensability argument, right? The whole point of the argument is to force you to be realist about those entities. In other words, you know, we may avoid commitment to the infinitesimals, but on the face of the indispensability argument, then the argument loses its bite, right? It's no longer an argument that supports realism about the relevant entities. Is a second response, right? So you may say the following, maybe the indispensability theories may insist that indispensability considerations just give a weak reason to consider something as a potential candidate. So you're not really committed, just telling you, look, maybe you should consider being committed to those things, right? And the results committee will only hold until a best theory emerges. When you finally have something that really deserves the full-blown commitment, right? And look, an inconsistent theory may be fruitful as a guide to successful, you know, theories, and being consistent, the future theories will offer a better blueprint about where your actual commitments should be, right? So in the case of infinitesimals, their inconsistency is exactly what highlights the need for some consistent successor. And once that successor is formulated, well, then you have your commitments, right? So basically, the strategy is wait and see, right? Don't give your commitment just yet, given the inconsistency of the theory. All right. So in that sense, is yeah, maybe we are temporarily committed because we're using this notion, temporarily committed to something inconsistent. But we have to do that until a consistent successor emerges. So what Yasser was considering that path, right? So sort of it's the Wittgensteinian path of waiting, wait for things to clear up, right? And don't have any commitments, right? But of course, that path undermines the whole point of the indispensability argument, right? Basically said also don't be committed. Basically, just assume that you have to avoid commitment to something inconsistent. Right?
Is that like
yeah.
That's a legit case of because they would say that
no,
people can say that that's just a mistake, right?
Yeah. The daily theists, of course, will welcome that. Everybody else would say that we don't, right? That we shouldn't. The question is, then you need to square the fact that the entity they want to dispense with now has been indispensable for the formulation of the calculus, and that's what is causing this trouble. Now, what a response we have, right? Of course, this move grants the point of the original objection, right? If one takes the indispensability argument seriously, the presence of infinitesimal just leads one straight into parallelism, right? So whether this commitment will be revised later or not is beside the point, right? What the indispensability argument will force us is to be committed to the existence of these inconsistent objects in the important case. And that's exactly the objection to begin with. So it's a reduction of those approaches that aim to preserve consistency, right? So now, it may be argued that one should simply deny that the early formulation of the calculus provides the best theory of the world, thus deny the use of infinitesimal is even indispensable. After all, the fact that the theory is inconsistent, as I said, well, maybe clearly indicates that's not just yet the best theory, right? Now, the argument will go, a consistent alternative would be better because, well, it's non-trivial, secondly, it has content, and thirdly, involves no commitment to inconsistent objects that both have and lack some properties. Hence, we should wait until a consistent successor is formulated before having any commitments. Okay, that's the wait and see strategy, right? Now, the problem is it's unclear that the consistent alternative is actually better, right? After all, provided the underlying logic of the inconsistent theory is better consistent, you have exactly the same features as the alleged better consistent theory would have, right? In what sense? Well, it's going to be non-trivial. Secondly, it would have content because it's non-trivial, right? And only involves commitment to inconsistent objects if the indispensability argument goes through. So the objects are really needed to do the work as they were, right? Of course, there's one way. If you really don't want to be committed to infinitesimals out of allergy or whatever, right? You just avoid ontological commitment from your quantifiers, right? You separate quantifier commitment and ontological commitment. You say, look, we can quantify over things that do not exist, right? We do that all the time, right? So, for example, when we quantify average moms have 2.4 kids, right? Do I believe, suppose that I don't know exact number of moms, right, in a population. So I'm going to construct an average, right? Is such an object as an average mom, right? Obviously not. So we are quantifying over something, even though we don't think that the thing exists. So we could do the same thing with infinitesimals, right? So if that would have been better for Leibniz, right? So you could say, okay, I'm using these objects. They're very plastic. They're very useful and helpful for me to express what I want, but I'm not committed to their existence, right? I think that's clean and neat. Note that when you do that, you deny the first premise of the indispensability argument, because you're saying, I'm quantifying over things that did not be that the thing has to exist. I think that's the mistake of the argument. But then you have to let the indispensability argument go to the dust, right? All right. It may be argued that the early formulation of the calculus was not even inconsistent, right? So well, then, there's no dialetheism there, right? In fact, that's Peter Vickers' view in his book on inconsistency in science. He says, we have seen that the number of significant inconsistencies which exist in real science is far less than has often been suggested. The main examples of significant inconsistencies in this thesis are the later Bohr theory of atom, Newton cosmology, and to a lesser extent, the early calculus and Kirchhoff's theory of diffraction. But in each of these cases, it's clear that scientists don't avoid the conflict by changing their logic. As the case studies have shown, classical deductive logic is used. Nor does it seem plausible that scientists should handle these cases by changing their logic. All that might be said is that these cases can be reconstructed by changing the logic. But it's hard to see what understanding might be gained by such a reconstruction. So I agree with him in the following respect. The issue is not to change the logic. As I said, there are changes of logic that are ad hoc, and they should not be performed. But some changes might be needed for expressive purposes. And as I spend time trying to express, that's exactly the situation with infinitesimals, right? So we cannot just say that they are consistent as a result, right? By the way, the notion of well, okay. So the issue is not whether the logic is classical or not, whether you're changing the logic or not, right? If the underlying logic is classical and the theory of infinitesimal is inconsistent, what we get is triviality, and that's it, right? Whether you derive the relevant implications or not, it's immaterial. Your theory is trivial and has no content, right? It may be argued that infinitesimal fail to form a theory. So say, well, we don't even have a theory, right? All we are given is a bunch of rules of thumb, and hence there is no inconsistent theory to be applied, right? But that doesn't seem right either, right? Because it misses the point that it's not just an object, right? You have actually principles, as I laid them out. There are some rules, right, for the operation with infinitesimal. There is a logic, which is often left implicit, right? And there's an interpretation of the infinitesimal. In fact, there are two, right? One by Leibniz, the other by Newton. So we have all the requirements you want. You say, well, there was a theory, indeed, right? Which turned out to be inconsistent, right? For the reasons we discussed. So we cannot just dispense with the thing by saying there was no theory at all of those things, right? Also note that much of scientific practice we find also puts some additional pressure on the indispensability argument. And I think the fact that there's a fair bit of pluralism in scientific practice exactly highlights that, right? So as we know, there are different non-equivalent mathematical theories and structures that are equally adequate to be applied in contexts in which the indispensability argument goes through. And then you have a case of underdetermination, right? Familiar case, non-relativistic quantum mechanics, you can formulate terms of Hilbert spaces, matrices, von Neumann algebras, right? So, and they're non-equivalent mathematically, right? But you can formulate the theory in any of those things. Which of them is supposed to be indispensable, right? So they offer different pictures about what the world is like, right, at the mathematical level, right? Arguably, at least one of them, right, or some other piece of mathematics may be needed, but which of them is the correct one, right? Which of them makes for the best theory? Right? Similarly, in the case of the infinitesimal, right? As I mentioned, there are two different interpretations of them in terms of Leibniz or Newton views, fluxions, or in terms of curves. Which of them is indispensable, right? They are incompatible in terms of what they claim about the nature of infinitesimals, right? So it's underdetermined which of these things, granting that they are indispensable, which of them is the case, right? So that also, I think, puts some independent pressure on the indispensability argument, right? It seems to conflict with the pluralism that we find in science, right? So it's unclear what kind of ontological commitment the indispensability argument ultimately suggests that we should have. All right. So the indispensability argument, by forcing artificially a commitment to the best theory, right, or class of structures, I think conflicts with mathematical and scientific practice, right? Often, I think the science just leaves those things open, right? What the scientists are interested is, well, whatever structure that they can get their hands on to solve the problems. That's what they're interested, right? You know, the larger picture, you know, it's left undetermined, right? So to conclude, as I indicate, there is a fair bit of pluralism, I think, throughout scientific and mathematical practice. Involves pluralism about theories, right? Different formulations of the calculus, pluralism about interpretations, different interpretation of infinitesimals, pluralism about the underlying logic, classical or consistent, right? And I think reflection about the role of mathematical consistency in applied mathematics reveals that once this assumption is relaxed, indispensability theories either become dialethists, right, or they need to abandon the realism, right? I think the choice here is clear. Along the way, the significant role that anomalies play in mathematical and scientific practice has been highlighted, right? That's one of the points of going through this example, right? Inconsistencies, when they allow for the expression of possibilities and successful solutions of novel problems, and that's exactly what infinitesimals do, are hardly anomalies, right? They have a positive role. So we need to think of them as positive anomalies, right, if you want. But they're guiding research, they're allowing problems to be resolved, right? Now, the inconsistencies are only anomalous when the problem situation they are part for requires a requirement consistency, right? Because that will force them to triviality. And then we have a problem, right? Why should we take the consistent requirement as something that should be adopted across the board, right? Maybe that's also something that is context dependent as so much scientific practice. Thank you.